Good morning, everyone. As Sir has already introduced me, I am Dr. Adhishree from Birla Institute of Technology, Mesra, Patna, India. And I'm feeling very lucky that I'm getting this opportunity today to deliver one of my work in which I have used very efficient software EMTP. The topic is data-driven and machine learning based microgrid protection using EMTP simulation environment. So my area of research is microgrid protection, as I will give a little bit idea about it. Like today's power grid is expanding in a great manner, and we are going to add more and more PV based and wind based sources, because of course we cannot rely always on non-renewable sources. So therefore our power system is developing a lot of microgrids within it. So microgrid is a small part of our network, which is where the extra sources, that is the renewable based sources, are connected near to the load centers. There are various challenges for its protection system because the conventional way of power transfer has been changed with the introduction of microgrid. I have introduced a data driven approach for the protection, and in order to get those data, I have used that EMTP simulation environment. So these are the contents of my presentation, like why we need data driven approach. Then the system which I have worked, that is IEEE 15 bus system, and then its simulation model in EMTP environment. And then I will discuss what are the various model components, and then I will discuss about what is the scheme of microgrid protection, how it is going to detect the fault in two types of mode, or we can say the grid connected mode and islanded mode. These are the two operating modes of any microgrid. Finally, I will explain what is the overall data driven scheme, and in real time how we can implement that scheme using OpenRT platform. So first of all, why we need the data driven approach? So here, since we are talking about the protection scheme, there must be some disadvantage in the previous scheme. So previous scheme has the overcurrent relays, since microgrid is always a distribution side environment. So what is the problem? That the classical method of protection, we have to define various relay settings, and based on that we can update those settings, and then using relay coordination we can have some protection scheme. But what is happening, that there is an intermittent requirement of change in relay settings, and every time we have some change in microgrid topology, we need to change the relay settings. So therefore, to overcome those issues, I have introduced some data driven approach. And why we are able to do that approach, because in our real microgrid systems we have intelligent digital relays and phasor measurement units that has facilitated us to get those electrical signals, that is the voltage, current, frequency, phase angle, active power, reactive power, whatever parameter we are choosing, those quantities are easily available to us now in present microgrid system. So there, if we are able to get those data, we can use those data to define some new type of protection scheme. So this is the single line diagram of the test system that is under study. It has, since I told that it is a conventional system, 15 bus system, but here two DGs, that is distributed generation, has been introduced. One is synchronous based DG of 1.2 MV and another is PV based DG. And apart from that, of course, this complete microgrid form is connected to a main grid through PCC, which is called point of common coupling. In this system, we have 16 lines and 8 loads. and various buses has been numbered. So for this system, a scheme of protection has been defined. So the first of all, if we will go step by step, first of all, the thing was the requirement was to retrieve the data of this system. And the data which I have extensively used for this system is the bus voltages and the current flowing in the lines. So first of all, its simulation model was required. And I will say that EMTP is a very efficient software because it gives us a very real environment as it considers the transient conditions also. So this is the model of 15 bus test system. And here again, we have synchronous based DGs and power supply, various buses, loads, PV system, and various measurement devices also. And here, this one is the fault. And one by one, I will explain each components. So the first component is the synchronous based source, that is your synchronous generator. So in the EMTP model, you can define this is the symbol and this is the you will see this toolbox here. It will show the properties. So here you can define the various phases, the available voltage, what is the phase difference, what is the nominal frequency, the number of poles. And this is the advantage. I have used other softwares also, but I didn't get this much of flexibility where I can define and change every quite parameters as per my requirement. So this is just one window. We can change other parameters and attributes also. Then the second source, apart from synchronous based sources, are the PV system. So this PV system was already available in EMTP. However, it is available in a user defined format. So this is also a very great feature of EMTP where we can define any new user defined function or block. So here it has been coded here, and various parameters of a PV system like temperature, irradiance, and the frequency of operation, the megawatt requirement, the apparent power requirement, the number of series and parallel number of PV cells. So the flexibility is so much high that we can just change the values here and we can easily get various models of PV. So this was also missing in some another softwares which I have tried to work, but finally I landed with EMTP and there I found these options. Next is the transformer. uh, EMTP is having transformers where we can define like it is delta star type. And of course, in the properties, we can change what is its power, what is its frequency, what are the windings. And then load is the another component. And here the load can be modeled based on the parameters. Here are L and C properties of this is about the pi section line. First, this is not about load. First, this is about pi section. Okay. So pi section also we can define the transmission line parameters RLC, and that based on these parameters we can define the various length of this pi section line. Finally, the loads are there. So load, we can define the kilowatt requirement, kVAR requirement, the various, the voltage at which load is performing, what is the other frequency is there, whether it is an constant current based or constant impedance based. So in short, again, there is much flexibility where we can define a number of parameters. So this is the load. And finally, since my system is based off for protection application, so I need a kind of fault introduction. So fault, there is already some fault block in the EMTP environment, but still here I have created it through the combination of switch and a resistor and a ground system that creates a line to ground fault. Then once the complete model is over, we had the measurements. So voltage measurement was the major requirement in my scheme. So this is the block for voltage measurement, where you can just connect it at a point and it will give the three quantities of the all three phases A, B and C. So again you can define the various parameters. And since I needed the RMS value of these voltages, this block will give the instantaneous value, and we can connect this output with the RMS meter and it can give us the exact RMS value of that parameter. Finally, after adding all the components and measurement devices, this is the scope view. So there is a very nice scope environment where you can see a number of quantities which you want to see in the instantaneous manner. Okay, so this is the three voltages, and from here we collected these data and then implemented it for our scheme. So this was about the model. Now let us just quickly discuss the protection scheme. So we assume that the protection scheme is having various facilities such as central protection computer, PMUs, PDCs, that is phasor data concentrators, and strong communication channels, IEDs, and smart devices where the devices can interact with each other and all the data and information is easily accessible to us. So based on that, this is the scheme where the voltage, frequency, and current in real time is always being achieved at the central protection computer. So it will continuously calculate the average voltage and frequency deviation at a time. And if the deviation in frequency is continuous or perpetual in manner, we can say that there is a faulted condition. Otherwise, it is a normal case. And there are some conditions for fault which I will explain in next slide. If those conditions are satisfied, then it is taken as a fault condition. Otherwise, it is taken as a transient activity. And once the fault's presence is known and local relays are unable to perform, then the trip commands are sent through CPC, that is Central Protection Computer, to the exact lines in which the fault has occurred. So this is a very small glimpse of and flow chart of the scheme. Now, how does CPC calculates everything? So here CPC means the Central Protection Computer. So it basically calculates the change in voltage. And how does it calculate? So it takes the average of all the voltages in all the buses, k is the number of buses, and compare it with the nominal value. That nominal value is taken as 11 by root 3 because my complete system is working at 11 kV system as per the Indian standards. So it continuously compares with nominal value and uh, calculates this delta Vx, and delta Ft, that is changes in frequency, is also being calculated as compared to the nominal value. Then the algorithm starts with the calculation of under voltage and over voltage disturbance counters. Okay. So here there are two disturbance counters, which is CVX minus and CVX plus. These initially at t equal to 0, the value of these counters will be 0. And the idea is that these counters will start counting only when they will experience the faulted condition. If it is a fault, not a faulted condition, it is not going to experience it. So during the fault, it is expected that we will get some voltage disturbance also, and under voltage condition is expected when there is a fault, and over voltage is expected in the unfaulted line. Okay, so this CVX minus is defined by this equation, and it's basically starts the counter whenever this disturbance or variation in voltage exceeds some threshold value. So it exceeds some threshold value, and this is TVX minus. So this represents that the counter will not start until this value of threshold is achieved. So this is the maximum disturbance level of threshold for disturbance up to which we can wait and see whether it is a fault or not. If that threshold is crossed, this counter will start counting. So similarly, this counter will be used here and it will decide which fault condition is present. So for single line to ground fault, this condition is judged if it is true for one of the phases and for remaining phases this equation is true, then this is the condition of single line to ground fault. Similarly, for double line to ground fault, the situation is defined by this equation, and for three phase fault the situation is defined by this equation. So here this fr is the frame rate, that is the rate at which the PMU is sampling the data, that is 10K samples per second. So the important feature in EMTP was that we can we first took the voltage value and we fixed its the samples per second. So we can keep it same with this frame rate and we can use those data for further analysis. These are the threshold values. And finally, once this type of fault is known, then we can find that in which line the fault is there. Okay, so for that, instead of using the direct current value, the normalized value of current has been used. And this is the normalized current, which is the actual current by the nominal current. So this ratio, if this ratio is highest in some of the line, in the faulted line, this ratio will be maximum, and that line can be understood as the faulted line through the CPC. So we will be more clear with the results. So this is the result uh, of fault detection and isolation when we are in grid connected mode, that is the main grid is connected to the system. So in this one, double line to ground fault was simulated in EMTP in line 4 between bus 4 and 5. So this type of voltage status we got. Uh, so since it was in phase A and B, so phase A and B, you can see the del V or delta V is having a dip and the fault has occurred at around 3 seconds. So it is having a dip while the phase C is having an over voltage condition. So again, when CPC will analyze this data, then it will calculate the counters. So here the counter for phase A and phase B has started after the initiation of fault. Otherwise, before at no fault condition, it was 0. That is what expected. And using this counter and the previous formulas, we can get the fault detection time of 0.1789 in phase A and 0.1772 seconds in phase B. Finally, now once it is known that double line to ground fault has occurred, now the line number in which fault has occurred, that has to be known. So the normalized value. Now this detection has happened at some detection index, and that index is defined here. So that is the detection counter index. At that index, we can check what is the normalized current value. And here we can see that since fault is in line 4 and line 4 is having the maximum normalized current value. So from here, CPC will know that line 4 requires the trip command. So in this one, the detection time is this one and the faulted line is line 4. Again, the same principle has been applied for another case where it is single line to ground fault in phase A at 0.3 seconds now, and line number is 8 and it is 32 kilometers from substation, and here 25% DG penetration. So why I have changed these situations? In previous case, the DG penetration was 50% and still this scheme was quite well working in that case. So even if we change the parameters of the microgrid system, operating system, the given a scheme is going to work fine in this case also. So that's what we achieved. That if we have a single line to ground fault, then in phase A, then we saw the dip in voltage, and again the disturbance counter of phase A, B, and C all are drawn. So here we can see that for phase A, the counter has started, but for phase B and C, it is still at zero position because only phase A is experiencing the faulted case. So in this changed operating scenario also, the detection time was 0.1837 seconds after the fault inception. Now, the apart from grid connected mode, the microgrids perform in islanded mode also, which means that the main grid system is isolated from the microgrid part due to some issue, and the microgrid itself is able to operate within itself because it already has some small sources near the load centers. So again, in this case, the line 4, in line 4, the fault has been created and the average voltage deviation is plotted here. So again, we saw that phase A and B is having a dip and C is having an over voltage. The counters have started, and based on the equations, the detection time was like this. And line 4 was having the highest normalized value of current as compared to the other lines. That is, we have 14 lines, and in phase A and phase B both. So this information can be transferred to CPC, and CPC is able to trip the particular line. Now, after understanding what is the basic application. So basically what we did, our motto was that, a little bit I would like to explain, that when we are doing the change in relay setting parameter, the problem was that whenever we have change in mode, that is we are switching from grid connected to islanded mode, we have to change the relay settings. And also, if we are changing some mode of operation, like we are changing the DG penetration level, or some lines are out of service, so everything impacts the overall short circuit level of the model of the network. So for every cases, we need some relay settings, and automatic update of those settings are required in that case. So to avoid that, this scheme does not care if it is working in grid or islanded or with what DG penetration level. It can, it has to process the data and then give results. So the overall scheme, I would like to just summarize here that this is the system. What is the flow chart of the complete work? So first part is to collect the electrical signals or data, that is voltage, current, frequency, whatever data we want, and through the EMTP model. This is the EMTP model, and the data can be collected through the scope. Scope has a very nice feature that whatever data is there, we can directly save it in .csv format, because we want to process this data in some another platform, like I have used MATLAB for that. So we can use fetch this data in .csv format, and then further action can be taken. So this A, that is, here we have those data, the voltage data, and not only voltage, frequency, and whatever things we require, but from the model, we will get the measurements of voltages and currents. And further, we can utilize them to get another quantities. So once we get that data in the CSV format, we can utilize those equations. So those equations which I have defined, that can be applied over those data, like del VP can be calculated, FT can be calculated, used to informations, the counters can be calculated, and we can get these results. So this is again those results which I already discussed. So after getting the data from EMTP and CSV file and processing it through certain set of equations, we will get some outputs like this. And once we have these outputs, the judgment, the logic for the trip command can be applied here, and it will generate the trip command. So this is the basic logic of this complete work. Now finally, this is whatever thing which has been done previously up to this part will give us results on a simulation level, on a simulation platform. But whenever we are doing some simulation, we need some validation, and that the best way to validate it is to perform those things on a real-time simulator. So I tried to work my apply my uh, set of equations or this protection scheme using real-time OpenRT simulator. So again, in this one, how we do it, we can draw the simulation model, and the OpenRT can integrate, we can have integration of OpenRT using EMTP also. Okay, so through MATLAB or through EMTP, we can integrate this real-time simulator, and in the real-time simulator screen only, we can model this EMTP or 15 bus system here. So this model was developed in OpenRT. Of course, the platform was MATLAB in my case, but we have our EMTP RV is also having the same facility. Once we have this model with us, then user-defined functions can be described, like in MATLAB or in EMTP also we can define. So the purpose of this user-defined function is that we had various set of equations. As I told you previously, we need del V, del F, CV plus, CVX minus. These all things we need. So we need a block here where those equations are defined. And these equations will give us directly the outputs, what we know, what we want. So that is the user defined block here. Now we need to download all these information or this simulation model in the OpenRT platform. So this is the OpenRT compatible model where you have to define a master and a console. So uh, the master is there where you define the model. This is the microgrid model, and this master's block job is to connect all the outputs to the console, and this console is connected through the OpenRT signal communication. So which means that the purpose of these two blocks is to interconnect this microgrid model, whether it is in MATLAB or it is in EMTP, with the real-time simulator. And that real-time simulator is connected to the software through OpenRT signal communication. So basically what we are doing, we are defining a model which is very close to the real system, and this the data is being transferred to a real-time hardware simulator. So once we have developed this one, here is the picture where this is the OpenRT simulator, this is the system. So here again, this is the console and the master block, and all these signals that is designed in the MATLAB is now available in this OpenRT through the communication links. So now whatever output this simulator will give us, that will be seen either in this CRO, or we can directly retrieve those signal to some another hardware. Okay. So thing is that up to here, we have taken the data from this model, processed it, and the output we want to get from OpenRT instead of getting it from some MATLAB simulator or EMTP simulator. So that simulation part will be done by Opalati. So it will give a real-time signal. Now those signal has to be used to activate the relays. So the hardware for relays can be created using Arduino based relays. So Arduino is compatible with this Opalati, and we can design a relay, and the purpose of relay is just to receive the trip command from Opalati, and Arduino based relay will just trip itself, or it will generate the trip command or close some circuit. So that is again a hardware part. Now it will send a trip command to the Opalati model to open the desired circuit breaker. So here relay is being activated using the real-time signal that has been generated through OpalRT, and OpalRT has got this information from the simulation model. So again, this generation of trip command can be sent back to the model again, and the respective circuit breaker, which is designed for the particular location where fault has occurred, it can open. So basically, there is a hardware in loop in the complete process, and we are getting some information from this model, and we are able to trip some circuit breaker of this model using the real-time signals. So we did it in our lab and successfully achieved, and we saw that the tripping is happening for the associated lines. So with this, I will end my presentation. And overall, basically, I would again like to point it out here that EMTP RV has very much flexibility, and I am just a user of it. I have not explored many things yet, but whatever I have explored, it was very flexible and very user friendly software. So these are the references which I have used, and this work has also been published, and this is all from my side.